Moving on to chapter 4. So chapter 4 does build on chapter 3, which is kind of nice. So you can't forget your skills on how to solve a quadratic equation or the zeros of a quadratic function. We are going to use that here. And we're also going to use the skills of how to solve a rational equation. But we're going to progress up to polynomial functions, which means degrees that are, from 0 all the way up to infinity, and rational functions. We're going to be graphing those rational equations that we did before. So let's start off with polynomials. So first off, what makes something a polynomial function? Well, it has a degree that is a whole number. Okay, so it can have a degree of 0, 1, 2, 3, 4, and so on. So when you have a degree of 0, it'll be something like y equals 5. So y equals 5 is a degree of 0 because the exponent on the x is a 0, right? So you end up with just y equals 5, and that is a constant function. Linear, the highest exponent is a 1. So a lot of people say there's no exponent, but there actually is an exponent. It's an exponent of 1. Oops, sorry, I put it on the m instead of the x. Okay, and then a quadratic is the highest exponent of 2. Cubic is the highest exponent of 3. Quartic is the highest exponent of 4. Quintic is the highest exponent of 5, and so on and so forth. All right, well, how can I tell from a graph that something is a polynomial function? Well, polynomials have some common features. One is that they're always continuous. There's no holes or breaks in the graph. In other words, you can draw them without lifting your pencil, and they're smooth. No sharp corners. The other thing that's really important is that the domain of a polynomial function is that x can be anything, right? There's nothing I can't square. There's nothing I can't cube. In other words, there's no radicals and there's no x's in denominators. So polynomial function, here's a nice x squared graph, here's a nice constant graph, here's a nice cubic graph, here's a nice quartic graph. You'll notice they're just smooth, right? Versus these the non-polynomial functions, you get these sharp corners, right? These do have these sharp corners. Or maybe the graph doesn't start until -1, right? So this is a radical graph. This one is also radical, just FYI. So to be polynomial, the exponent has to be a whole number. 0, 1, 2, 3, 4. This is an exponent of 4/5. And if you remember your rational exponent rules, if you have an exponent of 4/5, the 5 is actually an index. So this is the 5th root of x to the 4, right? So this is definitely not a polynomial. It's a radical graph. And then a rational graph, you've got these sections, you've got these like non-continuous graphs, and we'll talk about those as we go on in the chapter. All right, so what determines what type of a graph it is? Well, it's the leading term. It's the term that contains the highest power of x. We call it the leading term. A leading term has a leading coefficient, so the number in front of the variable, and it has a degree, which determines the nature of the graph. So if I look at an equation like y, or f of x, is equal to 2x cubed plus x squared minus 5, the leading term is the whole term, including the highest, that has the highest exponent on x. So the leading term would be 2x cubed. The leading coefficient is 2, which we don't actually care that it's 2. We're not going to be vertically stretching these graphs by 2. What I care about is that this leading coefficient is positive. The degree is a 3rd degree equation, which is odd. So again, I don't actually care that it's a 3. I mean, that is sort of important, but what I'm going to show you is that odd graphs share certain characteristics. And then because it is a 3rd degree, we would classify this as a cubic function. All right, I want you to pause the video and try this one. If you feel up to it, you can do this one, but this one is a little bit trickier, but definitely try this one. So pause the video now. So hopefully you did pause the video. Okay, the highest degree or highest exponent on x is 4. So this is my leading term. Okay, sometimes they do like trick you by putting them out of order. Things should be written in descending orders of power, so the leading term should be written first, but sometimes the only way to trick you is to put the leading term somewhere else. So make sure you are grabbing the highest exponent on x. So the whole leading term is -3x to the 4. The leading coefficient is -3, which all we care about is that it's negative. And the degree is a 4th degree, which is an even. We call this one a quartic function. All right, I wish you could come through the video and tell me whether you got this one or not. This one's tricky. So this one I've written as a product of linear factors instead of expanded out as a polynomial function. So this one's nicely expanded out. This is before it's been expanded, which is super helpful. We love this form when we're graphing, but it's harder to see the degree. What you do is you think about what would it look like if it was multiplied through. So if we did x minus 2 all squared, we'd end up with an x squared. And then if we took that x squared and multiplied it by another x, it would go up to x cubed. So this one would actually have a leading term of 3x cubed. So this will always be the coefficient, right? And so we'll care whether this is positive or negative. And then to determine the degree, just count the number of x's. So 1, 2, 3. All right, so my leading coefficient is 3, which is positive. My degree is 3, which is odd. And we would classify this as a cubic function. All right, why do we care? Well, believe it or not, knowing whether it's even or odd and positive or negative tells us a whole lot about the graph. In fact, I felt like it was useful putting this in the video. I'm going to show you a Desmos demonstration. So I'm going to show you a bunch of odd graphs. So I'm going to start with just like y equals x, right? That's an exponent of 1. That's an odd degree. Y equals x cubed. Right? That's another odd degree. We could go y equals x to the 5. That's another odd degree. We could do y equals x to the 7, right? And then we can start making them super funky. Like what if I went y equals x to the 5 plus x plus 3, or sorry, 5. Okay, or what if I did y equals x cubed plus x squared minus 7. Right? So I could do different things to these. They don't have to be the basic odd graphs to show this, but what I want to show you is that these are all odd graphs. And my question to you is do they have anything in common? So if I zoom them out a bit, right? What do I notice about all of these graphs? Well, hopefully you notice that every single odd positive graph, so positive coefficient, odd degree graph, starts down here in quadrant 3 and ends up here in quadrant 1. Okay, it doesn't matter what happens in the middle. All of those graphs do that. Well, what about if I put a negative in here? So what if I say this is negative x, and this is negative x cubed, and negative x to the 5, and negative x to the 7, and negative x to the 5 plus x plus 5, and negative. So all I've done is given them negative leading terms, right? So the leading coefficient is negative. Now, instead of starting in quadrant 3 and ending in quadrant 1, they all start in quadrant 2 and end in quadrant 4. So it didn't matter what happened in the actual function. If the highest degree was odd and the leading coefficient was negative, it started in quadrant 2 and ended in quadrant 4. If you don't know what I'm talking about with the quadrants, this quadrant up here is quadrant 1, right? Positive, positive. If you're doing any physics graphs or economics graphs, you know, you always graph up in here. Then we move up. So this is quadrant 1, and then you go counterclockwise. Quadrant 2, quadrant 3, and quadrant 4. Okay, so just in case that wasn't clear. All right, let's make them even graphs. So what if I throw an x squared in front of here? What if I throw an x to the 4 in front of here? An x to the 6 in front of here? An x to the 8 in front of here, an x to the 6 in front of here, and an x to the 4 in front of here. Do they share anything in common? Well, if you look at all of these graphs, they're all going up, right? All the even positive graphs open up, just like a parabola, right? Positive parabolas open up. So if you look at the commonality, they all start up here in quadrant 2, and they all end over here in quadrant 1. So what do you think is going to happen if I put a negative leading coefficient, right? Negative, 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 negative. Well, it took them from all starting in quadrant 2 and ending in quadrant 1 to all of them starting in quadrant 3 and ending in quadrant 4. So we can make that generalization. We can say that according to the leading term test, we can determine the end behavior of our graph dependent on whether it's an even or an odd degree, and then depending upon whether the coefficient is positive or negative. So an even positive graph starts in quadrant 2, ends in quadrant 1. An even negative graph starts in quadrant 3 and ends in quadrant 4. An odd positive graph starts in quadrant 3, ends in quadrant 1, and an odd negative graph starts in quadrant 2 and ends in quadrant 4. Okay, now this isn't something that you are expected to have memorized, it's something that you're expected to understand. And what I mean by that is there's something on your formula sheet that can help you out with this. So if I open up your formula sheet, right, and we look at it here, I want you to notice that here's an odd positive graph. Starts in quadrant 3, ends in quadrant 1. Here's another odd positive. Starts in quadrant 3, ends in quadrant 1. So you have to know then that if you put a negative out front, it would be a reflection of the y values over the x-axis. So it would start in quadrant 2, end in quadrant 4. Start in quadrant 2, end in quadrant 4. Same thing with your y equals x squared graph. So this is your basic even graph. Starts in quadrant 2, ends in quadrant 1. If I put a negative in front, you'd have a reflection of the y values over the x-axis, and it would start in quadrant 3 and end in quadrant 4. Okay, so not something to memorize. Like you don't have to like quiz yourself like, okay, an even positive graph starts in quadrant 2, ends in quadrant 1. No, you know what a parabola looks like, right? And parabola opens up. Picture it, right? Give it a frowny face, right? Put a negative out front. It opens down. Think of a basic line for your odd graph with a positive slope. Think of it with a negative slope, right? And so these graphs will help you determine the end behavior. Okay, so what we're going to do is you're going to determine graphs from their equations. So you're going to be able to match graphs to the equation. So not that I'm asking you to graph these yet. I'm just asking you, hey, if this is the equation, which graph could it be? And before we do that, one other valuable piece of information can be the y-intercept. The y-intercept is super easy to solve for because all you have to do is let the x value equal to 0. So it can give you one other piece of information about a graph that's easy to find. So what I want you to do with these, I'll do A, and then I want you to finish the rest of them, is I want you to look at it. So this is my leading term. It's even and it's positive. Okay, I don't care that it's a 4 and that it's a 3. I care that it's an even degree and it's a positive coefficient. That tells me that it's going to start in quadrant 2 and end in quadrant 1. So just from that information, I can look at these graphs and be like, well, which graph starts in quadrant 2 and ends in quadrant 1? D. Oh, okay, well, that was pretty easy. There was only one of them. You only really need the y-intercept if there's more than one graph that starts in quadrant 2 and ends in quadrant 1. You need some other defining feature. So to find the y-intercept, you simply let x equal to 0. So if I let x equal to 0, 3 times 0 is 0, minus 2 times 0 is 0. In other words, all the x terms go away, and I'm left with just the constant 3. So I can double check. Ooh, yep, that guy has a y-intercept at 0, 3. All good. Okay, so I want you to pause the video, and I want you to try to identify which graph belongs to each of these functional equations. Okay. So hopefully you did pause the video. A student told me once, count to 5 after I say that to give you a chance. Okay, so if you're looking at this one, hopefully you found that this was odd positive, so it should start in quadrant 3 and end in quadrant 1. Maybe you also notice that the y-intercept is 1, but the only graph that starts in quadrant 3 and ends in quadrant 1 is graph A. This one, it's an odd degree with a negative leading coefficient. So this one should start in quadrant 2 and end in quadrant 4, and the only graph that does that is B. Maybe you went further to find the y-intercept, and if I let x equal to 0, gone, 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 I'm left with y equals 2, and so I can check. Ooh, there it is, 0, 2. I should do that with the 1 here. 0, 1. Right, it's just a nice point to check. All right, and then lastly, process of elimination tells me that this one must be C, but to double check, it is even and negative. So it's going to open, it's a parabola opening down. So it's going to start in quadrant 3 and end in quadrant 4. So that's the only one that does that is C. And then the y-intercept, if I let x equal to 0, 0, 0, 0, all gone. So I get a y-intercept of 0. And I double check. Oh yeah, look at that, 0, 0. All right, so that's the first thing to practice. So here's your questions to practice, right? Practicing that end behavior test. So if it's even positive, where does it start? Where does it end? Can I also find the y-intercept? Give it a go.